Welcome back, everyone. Today, I'd like to go on to chapter 26, which is another biochem chapter, this time on proteins. Our main focus in this chapter is, as always, in every other chapter of the book, biochem or otherwise, we're going to be looking at structure, reactivity, and where appropriate and possible, mechanism. So we're not going to be considering biological function very much. I will leave that for your biology and biochem classes. That being said, my hope for all of you is that when we're done discussing chapter 26, you have a solid understanding of the structure of individual amino acids and also how they join together to make polypeptides and proteins. Again, this, I think, will be very helpful background for those of you going on in biochemistry. So to start off, it's pretty easy to consider what an alpha amino acid, which these are all going to be. Other amino acids besides alpha amino acids do exist, but all of the so-called protein-bound amino acids in nature are alpha amino acids, meaning that the carboxylic acid carbon and the carbon bearing the amino group are right next to each other. So they're attached directly to each other. And all of these are going to be compounds of this type. At least this is how the compound would look in the gas phase. Ordinarily, naturally, we're not dealing with things in the gas phase. We're dealing with aqueous solutions, mainly, of course, in biological systems. And so in aqueous solution, or also how the compound appears in the pure solid crystalline form, will be this zwitterion, where the carboxylic acid group is deprotonated and the amino group is protonated, at least near pH 7. And a couple things before we go on. First of all, in these structures here, and also these two in a moment, which I'll get to in a moment, these structures are shown without considering stereochemistry at all. We'll add the stereochemistry on in just a moment. And second of all, over here, we have the way the structure appears at pH 7. We'll also look at pH 1 and pH 14. Owl will occasionally be their usual evil selves and ask you to come up with what the structure would look like at pH 10.8 or pH 5.1. I think that's going a little too far. However, as I hope to prove to you guys, the structures at pH 1, 7, and 14 are always very clear. The only complicating factor is what is on that group R. Is that also an ionizable group that takes on different forms? So we'll show some examples of that in a little while. I also noticed I forgot my lone pair on nitrogen over here, so we'll just go ahead and add that. Good. So leaving aside again the issue of stereochemistry just now, what happens at an acidic pH, at a pH of 1? Well, that involves understanding the pKa's of the different ionizable groups, of which there are, of course, 2 in this structure. And I think you'll find, though of course I don't expect you to memorize particular ones, I think you'll find that the pKa's of the carboxylic acid functional groups on amino acids are generally round and about 2 or 2.5, which might sound surprising at first, actually. That's a good bit lower than most of the ordinary carboxylic acids we've been running into. I think acetic acid is a pKa somewhere between 4 and 5. So they can be up to 1,000 times more acidic. I can only think that's the effect of the neighboring amino group that's in the same molecule. It enhances the reactivity of the carboxylic acid group because, of course, the amino group is basic. So the pKa of the conjugate acid of these amino groups, as you see over here, remember pKa's only and always apply to acids, never to bases. So we have to look at the conjugate acid. And I think you'll find if you look these up, they're always round and about 9.5 or 10. And that gets us, by the way, to the idea of isoelectric point, which is something that will become important in biochemistry, something I'll probably emphasize quite heavily, something which I'm only going to emphasize much less heavily, but the isoelectric point of any compound, not just an amino acid. It doesn't apply just to amino acids. You can use that for any ionizable compound. At least I think you would only bother doing so with an ionizable compound. In any case, the pKa of the species is defined as the pH at which the solution of the species in question has an overall charge of 0. So you can, figuring out the isoelectric point for a simple amino acid where the group R is not ionizable, so like an alkyl group or something similar, that's not going to change ionization states in aqueous solution. All you do is you average the pKa's of the carboxylic acid of the group of the amino acid in question and the ammonium group of the amino acid in question. So you can see 2.5 and 9.5. We can do all this in our head. That makes a total of 12. 12 divided by 2 is 6. So you'll see the pKa's of most amino acids, at least with non-ionizable side chains, generally rounded about 6, maybe 6.5. It becomes a lot more complicated to calculate that when the R group is ionizable, has itself a carboxylic acid group or an amino group or something like that. And so I'm going to leave that for your biochem classes, because they'll probably talk about that there, but I don't think that's something worthwhile for us to focus on. So then, these are the structures at the 3-8 pHs, which I think are very clear. At pH 7, you'll always find the zwitterion form, again, give or take what might be going on with the R group, which we'll get to later. At an acidic pH, well, now we're below the pKa of both the carboxylic acid and the ammonium group, well below that of the ammonium group. So both of them will be protonated. The carboxylic acid will exist as the free acid, and the ammonium group will also be protonated. So you can see, again, assuming a non-ionizable side chain, the molecule is an overall charge of +1. What about at pH 14? Well, now we're above the pKa of the ammonium ion, and also very far above the pKa of the carboxylic acid. So both of them will be deprotonated at pH 14. So this might be a good time to do a quick review of your Gen Chem and understanding what the pKa signifies and thinking in terms of ionization states at different pHs. So again, at pH 14, that's always very clear. That's going to be above the pKa of all of the ionizable groups. So again, assuming a non-ionizable side chain at pH 14, we can count on the structure having an overall charge of -1, as you see here. And so there are 20 protein-bound amino acids. In other words, 20 different possibilities of R. I have a nice little table, if I can move my strange face out of the way over here. I just did a Google search for amino acids with structures. Until I added with structures, by the way, I got some really bizarre looking things where they didn't even draw the carboxylate and ammonium groups right. So be careful what you get when you do your Google search. But these are the 20 amino acids. And just before we go on, you will not have to memorize all 20 of these, not for my class. Those of you going on in biochem, you will have that pleasure, I'm quite sure. So those of you not going on in biochem, congratulations, you're going to dodge that one. I guess I would say, what if you memorized 1? Certainly you don't need to memorize all 20. What about 1? We can do 1. What about the easiest one? The easiest amino acid to memorize. How about glycine? It's the only one that's not chiral. The R group is H, so this middle carbon is just CH2. So that's the only amino acid that's not chiral. Just let me check my notes, make sure I'm not missing anything. Good. So as you see in your class notes, you'll find a table somewhat similar to this in your textbook. That will also help you get an idea of how to categorize the different amino acids. You have those with alkyl side chains. These are going to be non-ionizable, and also the side chain is quite nonpolar because it's just an alkyl group. Lysine also falls into that category. We have two that have alcohol functional groups, serine and threonine. Those, of course, are non-ionizable also. Remember, alcohols have a pKa way up in the upper teens. So even at pH 14, those are not going to be deprotonated. It's not alkaline enough to pull off that proton. We've got another one, cystanes, a really important one, talking about disulfide bridges. We could talk about how that affects the structure of proteins. We could talk about how when you get your hair permed, I don't know if people still do that. I just wish I had enough hair that I could get a perm if I wanted to. But alas, that's gone forever. Anyway, remember that thiols are quite a bit more acidic than alcohols. So this thiol, I don't know the exact pKa of the sulfhydryl group in cystine, you could look it up, but I'd be willing to bet it's round and about 9, maybe even a little bit less. So certainly this will be deprotonated at your higher pHs. Methionine also contains a sulfur, but this now is a sulfide, so this is again non-ionizable. Fairly polar though because of the sulfur. Proline's an odd one, isn't it? It's the only one where the side chain and the amino group are connected to form a 5-membered ring. So that will certainly have its effects on protein structure. Phenylalanine and tyrosine both contain aromatic rings, and really so do histidine and tryptophan. If you work this out, how we did in chapter 16, I think you can convince yourself that the so-called indole group here on the tryptophan and the so-called, oh, come on, Jack, imidazole in the histidine, these are both aromatic rings. In the case of tyrosine, of course, we've got a phenol also. So remember, those are also quite a bit more acidic than aliphatic alcohols. I think you'll find that pKa is round and about 9 or 10. So that will also be ionizable, and you will be removing that proton at pH 14. 2 of the amino acids have carboxylic acid groups in their side chains. So those also have quite low pKa's, I think again around 2 or 3. At pH 1, of course, everything here will be protonated. I think you'll find then the overall molecule is a charge, now let's see. Yeah, I guess it will again be +1, right? Because the carboxylic acid groups will all become neutral free carboxylic acids. 2 of them, 2 of the amino acids have amide functional groups. So those are correspond to the carboxylic acid ones, just as you have aspartic acid and glutamic acid, you have asparagine and glutamine. Those are the amide versions, if you will, of the 2 carboxylic acids. And then we have these 2 oddballs, lysine and arginine. So lysine has an amino group at the end of a fairly lengthy alkyl chain, and this arginine group, this guanidine group as it's called, that happens to be the most alkaline organic functional group. So you'll find the pKa of this ammonium group here, this iminium group, is quite high. And so you'll again need to go all the way up to pH 14 almost before that gets ionized, or rather before that gets deprotonated. You go just to C double bond NH. One thing this chart is not showing at all is the issue of stereochemistry. So over here, I'm showing you how natural amino acids look. Natural amino acids are in what's called the L form. So that means they will always have this stereochemistry. And here I'm showing you 2 different views of the molecule. To get from one to the other, we've flipped it over, essentially. And that's going to be important. You're going to need to know both of these types of structures. That will become quite important in a moment when we start drawing amino acids. So that being said, just by way of a little comic relief, I can actually draw amino acids with 1 click using ChemDraw. You're going to be so jealous. So let's see, let's do, which is this one? It's a little, let's do leucine. So I can just go, and to bring it onto the screen so you can see it better. seems they're drawing the gas phase form. So, and of course, they're also not showing the stereochemistry. So it's not all that useful. It's just very fast. But we won't draw them that way. I will expect you guys to be able to draw not just single amino acids, but also small polypeptides with the correct stereochemistry. And so we'll learn how to do that very shortly. So, so it's important to remember both of these general structures for amino acids. And again, here I've drawn them at pH 7. I would expect you, again, to be able to do so at pH 1 or pH 14. No other weird pHs, I don't think. I don't think that's worth your time. But again, at pHs 1, 7, and 14, it's always very clear. So I think those are worth knowing. Next, in order to connect two amino acids, the way that's done is by connecting the carboxylate group of one with the amino group of the next. And so you'll get an amide functional group. And that will always be the case. That's invariant. So I expect you to know what an amide functional group looks like. And so if I'm clever, I'll be able to do this with structures, or with colors, rather. So we'll put our carbonyl over here. And then the chain will continue over in this direction. And then over here will be our amino group nitrogen. And that will connect to the next amino acid residue. So that connection is invariant. That's how we connect the carboxylic acid carbonyl carbon of one amino acid to the amino group nitrogen of the next one. So if I were to use a bit of color over here, let's make that part of it red. So this portion would represent the carboxylate carbon of one amino acid connecting to the amino group of the next one. And this is done by nothing other than a nucleophilic acyl substitution reaction, like we just talked about in chapter 21. Of course, under normal circumstances, you can't react a carboxylic acid with an amine and hope to get an amide. Carboxylic acids are just too unreactive. In the lab, this can be done, though, if you add DCC, dicyclohexyl carbodiamide. Recall that I said we were going to put that reaction off to chapter 26, and so here we are in chapter 26. Of course, in living systems, there's no DCC around, so there's an enzyme that does that for us, that carries out that coupling reaction to connect the carbonyl of one amino acid to the amino nitrogen of the next one. So that being said, I think we are ready to draw our first polypeptide. And I have your class notes open here. The example I have in there is serine alanine glutamine, or serine glutamine, or is it glutamic acid? It is glutamic acid, my apologies. So, and again, I don't really care if you memorize the 1 or 3 letter codes, though they both are used quite frequently. Of course, in any exam situation, I would give you what these side chains are. Who knows, I might even just give you something like this. I still have to think more about how exams are going to work. Luckily, I have a bit over a week. And also, fortunately for you guys, I'll have had my Chem 222 exam before yours. So I'll hopefully have ironed out at least some of the kinks. So I'm just going to make a long chain here, like this. And I might, yeah, this is fine. So, oh, this reminds me. Let me see if I can do an undo. Yes, good, that's all still there. So I mentioned that this chirality here is always going to be what you see here, always the L form. And I got to thinking, gee, how does that work out with R's and S's? You know, and the interesting thing is, this configuration will sometimes be R and sometimes be S, depending on what the side chain is. And I'll show you what I mean. I just thought this was endlessly fascinating. And I can also show off the magic powers that I have in ChemDraw. I can do show stereochemistry. So that's S. So this would be alanine over here. What if instead of alanine, we had cysteine, CH2SH? Well, that sulfur now is going to throw everything off, because that's going to now beat all of the other atoms. And so that will now be in the R configuration. So that probably is why they do that. It's interesting, though. Some of these are in the R configuration, some in the S. But all of them are always in what's called the L form. Couple more things about the L form that I realized I forgot to say. One is D-amino acids certainly do exist. You can buy them. They just are not natural. You don't find them in living systems. They're unnatural compounds. Another thing that I want to stick in the back of your minds, because it's one of these unfortunate things that we're stuck with, whereas it's the L-amino acids that are the natural ones, unfortunately, when we get to the carbohydrates chapter, you'll find that it's the D sugars that are the natural ones. So it's L-amino acids and D sugars that occur in nature. The opposite ones, they're enantiomers, do exist. They just are not natural. They have to be made in the lab. Good. So let's go back to what we were doing before. I'm just writing SAG, serine, alanine, glutamic acid, just to remind myself. I know the side chains, and even if I didn't, I guess I have them right over there. But I'm just you can get an idea of at least one possible way to phrase such a question in your class notes. So I'm just writing that up there just to remind myself. Let's again make a nice long chain. I don't know if I'll need all those, but we'll see. So I think it also says it's certainly reasonable to start at pH equals 7. So let's go ahead and do that. So remember again, by convention, we always start with the nitrogen terminal, and we work our way to the carboxylic acid terminal or carboxylate terminal. So there's the amino group of our serine. And I remember, you can find out yourself if you rewind the video, in this configuration, our R group is going to be on the wedge bond and our hydrogen on the dotted bond. So the side chain for serine should be CH2OH. Just let me double check. Yep, there it is, CH2OH. And again, thinking about pKa's, that OH group is going to stay protonated. Again, pH 7, even pH 14 is nowhere near alkaline enough to deprotonate that alcohol. The next carbon over is going to be what had been the carbonyl group in the carboxylate. And so that's going to be C double bond O. Next one over is going to be the amino group on the next amino acid. So I'm just going to write NH, because that's always going to be a hydrogen. It's always going to be a secondary amide. And so the next carbon over is going to be our chiral carbon on our alanine. Actually, I think I already have it. So now, since this is pointing down, this is in the other configuration, you can again go back and verify this. Now the hydrogen is going to be on the wedge bond and the R group on the dotted bond. And so the R group for alanine is just methyl. So I'm already done. And then we again move on to the carboxylate carbon and what had been the carboxylic acid group in that amino acid. What have I done? Exciting. I prefer the octet rule myself. Okay, I actually kind of want to color code some of these. So this first one here, that's going to be from the serine residue. What color do you like? We'll leave that one black. And the next one is going to be from the alanine residue. So that's going to be this whole piece, like that. And maybe we'll call that, color that one red. And then we'll move on to the next residue, and we'll give it a color also. So next comes again the NH of the amino group of the next amino acid. And then we have our chiral carbon. We need a wedge bond and a dotted bond. And now again, on this carbon, the hydrogen is going to be in back, and the side chain, the R group, in front. So this is glutamic acid. This is the longer carboxylic acid, right? Aspartic acid is CH2CO2H. So this one should be CH2CH2CO2H. Well, what am I doing? I can check. Glutamic acid. Yep, here we go. C2CH2s. So that's that. Oh wait, whoops, I lied. Not CO2H, of course, CO2 minus, right? Because we're at pH 7. And at pH 7, we're above the pKa of those carboxylic acid functional groups. And then finally, you've got the terminal carboxylate ion of that amino acid. So let's now color that some other color. Maybe green. And then, if you want to think of it that way, let's color the two peptide bonds, the two amide bonds, blue. There you are, one very colorful tripeptide. That green is hard to see. Let me see if I can make that a different color. That's a little easier to see. Well, yellow and pink sure aren't going to be any better. Is this bright enough? Oh, it's even worse. I guess I'll just make it black again so that at least you see them separated. Good. How did I do? Let's see. Oh, that's great. I noticed in my class notes I have it flipped the other way. But CH2OH, NH, yup, then the methyl group, and then yup. So it's the same thing as what I have in the class notes. So drawing a simple, small polypeptide like this is something that I would expect you to be able to do. That's pH 7. How's that going to change at other pHs? I have the ability to do eraser chemistry. You might want to pause the video for a moment and think about that for yourself. Let's first consider pH 1 and how everything's going to change. So as I move from left to right across my polypeptide chain, of course, nothing here is going to change. pH 1 is not acidic enough to put a proton on any of these other atoms. The only ones that are going to change are these carboxylic acid functional groups. They will now be protonated to give the free acid. And so those will go to CO2H. So hopefully you wound up with something like this. What about at pH 14? Now it's going to change. Well, now our carboxylic acid functional groups are going to go back to carboxylates, because at pH 14 we are well above those pKa's. Recall they're around 2.5 or something like that. I don't see anything else changing. pH of 14 is not alkaline enough to deprotonate anything else, but it is also alkaline enough to deprotonate the ammonium ion and go from the ammonium ion to the free amine, the amine-free base. And so that's how the molecule would look at pH 14. So that sort of method of thinking it through, I would expect you to be able to do. So certainly review about pKa's and how pKa affects ionization state, and so on. You know, I actually am thinking, I was going to do this all in one video, but I think we've already done a lot. So let me leave the rest of the video for later. So we'll stop right here, and next we'll move on to consider things like how we can make amino acids in the lab, and also for the grand finale, we'll go over DCC coupling, which is part of how polypeptides are made in the lab. So we'll leave that there for now. Have a great day. We'll see you next time.